myself. Like to introduce myself before we get started on the workshop. So my name is Natalie Butterfield. I am a postdoc here at the Green Bank Observatory. I'm currently a third-year postdoc, so I've been at Green Bank for 3 years. I've learned how to submit proposals for the GBT, observe with the GBT, and so I wanted to share a lot of the information about proposing to use the GBT for the workshop today. All right, so just to kind of go over the goals of this workshop. So the goals for the workshop are to train new GBT users on how to propose for telescope time. So the types of information that you need to be including in your proposals, the type of different observational setups, different observing modes that we have available, just so that way you can get the best science possible from our instrument. It's also to update the community on the current GBT capabilities. So the GBT capabilities can vary across different proposing sessions and cycles, depending on new receivers that come online, different types of bandwidth, different types of instruments that we have available. And so just to kind of keep the community up to date on the current capabilities for each proposal cycle. And then lastly, to also address questions and assist users with submitting GBT proposals. So that's why we're here. That's why we have the scientific staff, is to be able to help you all, the community, be able to submit your proposals and address any types of questions that you have or any concerns that you have with submitting a proposal or anything that you just aren't very familiar with. That's why we're here. We want to help you be able to get the best proposal submitted and the best type of science capable. So just to kind of cover a summary of the workshop schedule. So this first talk is just going to cover an overview of the different GBT science capabilities, as well as the different capabilities that we can do with the GBT, as well as the current proposal cycle as well. Then we will cover the proposal submission tool. So that's the online PST, which you will be using to submit your proposals for the GBT. And then we will cover the sensitivity calculator, which is one of the tools that we have available to calculate how much time you would need on source. And then following that, we will do the mapping calculator, which is another tool that we have available, which you can use to estimate how much time you would need to map a larger region of the sky if your source is extended. And then lastly, we will wrap up by doing an overview of the new Helpdesk, as well as covering just some general tips on a good proposal, different types of information that would be helpful for submitting a proposal, and then just any types of additional discussion that arises over the workshop. So we will be trying to stick to this schedule as closely as possible. That way, if anyone is interested in just attending the sensitivity calculator talk, that they can be on from 3:30 to 4. So we will be trying to keep with the schedule as closely as possible. But we do have that additional discussion at the end in case there are questions that we were unable to answer during each one of these time slots. I'd also like to note that there's going to be a second workshop on Tuesday. So this next Tuesday, July 27th. From 9 to 12. So you'll notice that this has a slightly different time from the 2 to 5 session that we have today. The main reason why we wanted to have these two options was to cover a larger area of the community. So if there's someone who lives on the West Coast versus Europe, that we have a range of times that would better fit those different time schedules. So there will be a second workshop on Tuesday that's going to be held from 9 to 12. And again, it's going to be a very similar, identical workshop that we have today, but if you're working through your proposal over the weekend and you're still not quite sure about the sensitivity calculator, feel free to sign up for that talk on Tuesday as well. And again, we will be keeping with this schedule. So you should be able to know what times you would need to log in to attend that talk. Okay, so that's kind of an overview of the workshop. So just to cover some of the GBT overview and current capabilities. So an outline of the talk for this is going to be just a basic overview of the GBT. Then I'm going to briefly discuss all of the different types of science areas that we can study with the GBT, cover some of the capabilities and performance of the GBT, and then cover several of the different observing strategies that you will need to know for submitting a proposal. And then lastly, wrapping up with the current 22A proposal call. All right, so just a brief background on Green Bank as a site. So Green Bank is the original NREO site and has been operating for nearly 60 years. We have several telescopes on site that have been commissioned over the last several decades. But the GBT is really the bread and butter of the Green Bank site. That is the main telescope that we use for a lot of the science on site. It was completed in 2000. And we had some improved surface back in 2009 to help with higher frequency observations, so up to 3 mm observations. The GBT is located in what's known as the radio quiet zone. So there's two different types of radio quiet zones. You have the national radio quiet zone, which is shown over here, where you have this larger region that covers both West Virginia and Virginia. So this is the national radio quiet zone. And so there's two main sites within the national quiet zone. So you have Green Bank, which is shown here with the GBT. And then you also have Sugar Grove, which used to be a naval site. Now within the National Radio Quiet Zone, you have the West Virginia Radio Zone, which is about 10 miles or so around the observatory. And it's just organized by West Virginia. So the purposes of having a radio quiet zone are to reduce the RFI interference. So now we do still have some RFI signals. A lot of these tend to be from satellites, and you can't really do a whole lot about that. But at least within these quiet zones, there is a reduction of cell phone towers, microwaves, Wi-Fi routers, anything that can be producing a signal that could interfere with science observations. So that's why it's known as the radio quiet zone, is because we've reduced a lot of the radio interference. However, especially at lower frequencies, you still can get some radio interference, but a lot of those tend to be from satellites. All right, so the key capabilities of the GBT. So the GBT is shown over here, where you have basically the signal path. So it has a 100-meter unblocked dish. So that means that the feed arm, or the arm that's supporting the receivers, is off axis. So you don't have a lot of these types of structures that you get where you have the receiver sitting directly over the center, and you can get a lot of side lobes and a lot of artifacts in your images. And so the GBT has an unblocked aperture, which can help a lot of the imaging. The receivers cover from about 0.1 to 116 gigahertz. So we cover almost 2 orders of magnitude in the frequency part of the spectrum. And so you can see down in the bottom image down here, just the coverage of the frequency space for the GBT compared to the VLA and ALMA. So we do overlap a bit with both of the other NREO facilities, so the VLA and ALMA, and we extend down to a much lower frequency range as well. So we have excellent point source sensitivity. The large collecting area of the GBT allows for high sensitivity for both point sources and for extended diffuse objects. So if you're looking at faint H1, for example, in distant galaxies, the GBT is an excellent image instrument for being able to observe and image some of that diffuse gas. Because it's a movable structure, we're able to observe about 85% of the total sky. So we can get down to declinations of about -46 degrees. So we can observe a large area of the sky coverage using the GBT. And as I mentioned, it's located in the National Radio Quiet Zone. And so RFI is reduced compared to some of the other radio sites. So as I had mentioned, there were some improvements to the surface dish. So the GBT dish has what's known as an active surface. So what does this mean? So for the GBT, you'll notice that we have all of these different panels, which are shown both in the top and bottom images here. So it has all of these different panels that make up the primary dish. And so at the corners of each one of these panels is an actuator. So there's 2,000 or so actuators across the surface of the dish. And so what these actuators do will allow us to change the surface structure. And so being able to change the surface structure allows for high frequency observations, so up to about 3 mm observations. And so on a good night, we can get an RMS on the surface dish of about 200 microns at night. All right, so just to kind of cover some of the last few overview topics on the GBT. So as I mentioned, it's fully steerable, both in azimuth and elevation. So the top image here shows the what the GBT is sitting on. So it has this track, and the GBT will rotate in azimuth along this track. And then it has a, where you can see the tilting structure. And so it can tilt both in elevation and rotate in azimuth. So it's fully steerable. Unlike several of the other, larger dishes such as FAST or previously Arecibo, where you had the dish sitting in the ground, the GBT can actually tilt and rotate and observe about 85% of the entire sky. So we can observe down to an elevation limit of about 5 degrees or so above the horizon. We are sitting in the mountains, so we do have, we're surrounded by mountains in the surrounding area, and so the elevation limit that we have for the GBT is about 5 degrees above the horizon. However, I will mention this later on in the talk. If you're observing at several of the higher frequencies, especially around some of the water lines, then you probably will want to go to a higher elevation than just 5 degrees. You will probably want to have a minimum of at least 15 or 20, but we can go down to an elevation limit of 5 degrees. And then I've also included several of the slew rates that we have for azimuth and elevation, just to keep in mind if you're pointing to a different portion of the sky, you do have to take into account how long it will take to slew across the sky to your different sources. Okay. All right, so as I mentioned, the GBT has a wide range of science areas. So we cover a lot of pulsar work, so discovery of new pulsars, detections of some of the most massive pulsars, gravitational waves using pulsar timing. There's a large project that's being run at GBT that's called Nanograv. And so that is a study where they are observing multiple pulsars to be able to determine or potentially detect gravitational waves using this pulsar timing. So there's a large project that's being conducted by the Nanograv team who have time on the GBT directly to observe these types of pulsars. As I mentioned earlier, neutral hydrogen. So the high sensitivity of the GBT allows for detecting several of these fainter diffuse structures, so like H1. And therefore you can determine the masses of local galaxies, understand the kinematics of the galaxy and local group, as well as dark matter, and to be able to observe the interactions between galaxies or the H1 between galaxy clusters. So high redshift in cosmology, we've observed galaxy clusters looking at CO in the early universe, H1 intensity mapping at high redshift. So we do a lot of high redshift work. And then one of the growing areas of astronomy has been astrochemistry, or looking at interstellar molecules. And so the high spectral resolution of the GBT allows for detecting several of these spectral lines all the way up through 3 millimeters, which are rich, can be rich in a lot of spectral lines. And so there's been several papers that have come out recently by Brett McGuire's group, which has used the GBT to detect some very complex organic molecules and TMC1. So if you're interested in that, please see some of his work. We've also covered a lot of work on masers, so looking at and understanding black hole masses by detecting the masers that are associated with the accretion disks around these supermassive black holes or black holes. The distances using proper motions to these masers, as well as independent measurements of the Hubble constant. We've also done a lot of work on understanding star formation. So using the KFPA receiver, which I will discuss later in the talk, There's been a lot of work done on mapping ammonia across the galaxy, especially some of Rachel Friesen's work for the gas study. And then also there's the Keynote survey. So that's both of those use the GBT to map ammonia across the plane of the galaxy. And then also understanding some of the cold dense gas tracers at 3 and 4 millimeters. We've also done some work on just understanding basic physics. So the search for gravitational radiation, limits on some of the fundamental constants. And then we've also done a lot of work with the solar system astronomy. So we have done some previous work with doing some planetary radar. So we have some very beautiful images of radar emission either from the moon or looking at asteroids. We've also been working with understanding some of the chemical composition in comets. So we've done some observations looking at some of the molecular lines that could be associated with outgassing from comets. And so we've done some observations on that as well. We've done a bit of work with SETI. This is what's known as the Breakthrough Listen project. So that is one of the projects that has guaranteed time on the GBT. And so they have been observing several nearby stars. And so we've done some work with SETI. And then lastly, some work with fast radio bursts. So recently we've had a connection with the CHIME array, and we've been working on setting up some telescopes that will be supporting the CHIME array, as well as understanding some of the repeating signals for FRBs, as well as their characteristics. So there's just a wide range of different science that we can do with just this single instrument. And this also shows up when we look at the distribution across the Astra 2020 decadal survey. So if you're unfamiliar with this, the Astra 2020 decadal survey was a survey that is currently underway. A few years ago, they had a call for white papers. So these are different types of science areas that the scientific community believed would be important over the next decade. And so it had different areas of science. So either planets and star formation, galaxy evolution, planetary systems. You can see the full list down here. But the real key takeaway point is that the GBT science can satisfy all of these, that we cover a wide range of different science just with our single instrument. And so just wanted to iterate that, you know, if you're interested in using the GBT for your science, we would be happy to work with you on how to make that happen. All right, so getting into some of the GBT capabilities. So this is just kind of a summary of some of the things that I talked about earlier in the talk. But if you are interested in proposing to use the GBT and you just kind of want a quick table that has all of this information, page 1 of the proposer's guide, table 1, is this table that's shown here. So it's just a quick summary of all of the different types of information for the GBT as kind of a takeaway point if you're interested in that. All right, so moving on to our available receivers. So we have 2 different types of receivers. So we have what's known as prime focus receivers and Gregorian receivers. So prime focus receivers are receivers that are attached to what's known as a retractable boom. So you can kind of see that structure here. And so if you're observing with prime focus, what happens is the operator will extend the boom, so the boom will sort of rotate out above the subreflector. And so you will be at your primary focus. So you have your light or your signal that's coming in, it bounces off of the primary dish and then is collected in the prime focus boom. So prime focus is typically low frequency, so less than 1 gigahertz approximately, and there can only be one receiver that is on the telescope at any time. You cannot have multiple receivers, mainly just because there is a single structure for that. Alternatively, we also have what's known as Gregorian receivers. And so these receivers use the subreflector. So the receivers are located in this cabin down here. You can kind of see L band sticking up above that. And so the signal that comes in from space bounces off the primary dish, the 100-meter primary dish, and then goes off of the subreflector, which is located up here and is reflected down to whatever is in focus in the Gregorian torch. So that will rotate and allow different receivers to be in focus, so up front, and that's where the signal comes in. Now, the Gregorian receivers are typically higher frequency, so this is frequencies above roughly 1 gigahertz or so, and it can hold up to 8 receivers on the telescope at any time. So you could switch between, let's say, L-band over to C-band in a single observing run, but you wouldn't be able to switch between different prime focus receivers because they have to be manually installed at different times. Okay, so just to kind of cover the prime focus receivers in a bit more detail. So prime focus has 4 main frequency bands in PF1. So these are known as the 300 megahertz, 450, 600, and 800 megahertz receivers. The full frequency range is shown here in the parentheses. So for the most part, typically over a proposal cycle, we'll alternate between roughly 800 megahertz receiver and the 342 megahertz receiver. The 450 and 600 don't usually go on the telescope too often, mainly just because there are these strong TV signals, which produce strong RFI. So if you are interested in submitting proposals for those receivers, you should contact a support scientist before submitting a proposal for those speeds. The receiver availability for the different prime focus receivers are very dependent on the amount of successful proposals or the A-list proposals that are submitted for different receivers. So if say, for example, 75% of the successful A-ranked proposals are asking for 800 megahertz, then that will be the one that is on the telescope more often than the others. So it is varying depending on different semesters, and that variation is dependent on the successful proposals that were accepted. So also there is PF2, which is slightly higher than the frequency ranges shown here. So this is about 0.9 to 1.2 gigahertz. The bandwidth options are from 20, 40, 80, or 240 megahertz. But I think in the 3 years that I have been a postdoc at Green Bank, I think I've only seen this receiver gone up once. So it's not likely to be scheduled for installation unless there's a very strong A-ranked type of proposal that comes in. So it's not likely to be scheduled for installation, but we do have that receiver for prime focus as well. Okay, so moving on to the different Gregorian receivers that we have available. So there's 11. Again, any 8 could be on the telescope at any one time, but we do have 11 Gregorian receivers. We have several low frequency receivers, so like L-band, S-band, C-band. These are typically on the telescope all the time. L-band is huge, and so it's hard to bring that down or put it back up. And so usually L-band is always on the telescope unless there's some unknown issue that we run into or something like that with those. But for the most part, all of the low frequency Gregorian receivers are on the telescope 24/7. There's a few details for some of the different receivers. So for example, with L-band, which covers about 1 to 2 gigahertz or so, we have a notch filter that you can select either in your observing mode or in your observations. This notch filter is from about 1.2 to 1.3 gigahertz, and basically it just blocks out a part of the spectrum where there's very strong RFI. And so that can help with your baseband or your bandpass to be able to exclude some of that RFI by including this notch filter in there. So if you see notch filter come up when you're looking at L-band, that's basically what it means, is that it's just suppressing some of the strong RFI that's in the frequency band. Then we have S-band, which is about 2 to 3 gigahertz, C-band, which is about 4 to 8 gigahertz or so. Right now, we've been having some issues with the circular polarization for C-band, so we recommend that people who are proposing to use C-band go with linear polarization only. So that's what that note means. X-band, so we also have X-band, which covers about 8 to 12 gigahertz or so. However, we wanted to note, and again, this is also listed in the proposer's guide, that the polarization purity degrades above 10 gigahertz. So you can observe up to 11.6 gigahertz, but just be aware that if you're trying to do polarization observations, that the purity degrades as you go above 10 gigahertz. And then we have some of the higher frequency, and you'll notice that all of the higher frequency bands have either 2 beams or multiple pixels, multiple beams for all of these receivers. So we have KU band, which operates from about 12 to 15 gigahertz. We also have the KFPA receiver. So KFPA stands for the K-band focal plane array. So this is a multi-pixel receiver. We have 7 pixels associated with this camera, which makes it very good for any type of mapping, because you have multiple beams across the sky, so you can map a larger area relatively quickly. For KFPA, there's 2 different types of observing modes. So you can have narrowband mode and broadband mode. So narrowband mode, the largest or the widest maximum bandwidth that you can get is across 1.8 gigahertz. And so usually if you have narrowband mode, that's if you have multiple pixels. So if you want to take advantage of using all 7 pixels, then you will be limited by this 2 gigahertz or so maximum bandwidth for where you can place your lines, where you can place your spectral windows. Now, if instead you wanted to maximize your bandwidth, maybe you have a point source and you just want to target that point source with as much bandwidth as possible, then you can do that as well. You can get up to 7.5 gigahertz maximum bandwidth, but again, you are limited to only use 1 pixel for that. We also have the KA band, which covers 26 to about 40 gigahertz. And KA band is actually broken up into 3 different subbands. And so those subbands are listed here. So if you wanted to observe at 27 gigahertz, for example, and you wanted to observe at 32, you would have to have those set up as 2 different resources in your observing setup, because they are broken up into these 3 different subbands. Q band covers from about 39 to 50 gigahertz. And then we have some of the higher frequency bands. So W band, which covers 67 to 93 gigahertz. And similar to KA band, this one also has several, or is broken up into 4 subbands as well, which are listed here. We also have Mustang 2. So Mustang 2 is a bolometer camera. This is commissioned by the University of Pennsylvania. And if you're interested in using Mustang, which is a continuum, essentially a continuum observation, that you need to have permission from the Mustang team to use this. And so if you're interested in using Mustang, please drop either a comment in the chat or Q&A box, and we can pass you the information on how to contact the Mustang team for them. Lastly, we have the Argus instrument. So Argus is a multi-pixel receiver, so it has 16 pixels. And because it has 16 pixels, there is only a single polarization for those observations. So just be aware that if you are using Argus, that you have just a single polarization for those observations. All right, so that's just kind of a brief summary of all of the different receivers that we have available for in the Gregorian turret as well. Okay, so I know that was a lot of information, but if you are interested in using any one of the types of receivers that we have here, please view page 10 or table 3 in the proposer's guide, and a lot of this information, including the frequency ranges, the receivers that have the different subbands, different types of polarization information, polarizations per beam, all of that information is included in this table 3 in the proposer's guide on page 10. So we cover a lot of, the information here, as well as this is a continuation of table 3 where we include information about the bandwidth cover, the full width have max, so basically what the beam size is for the different receivers, separation for the different beams. So as I mentioned, a lot of the higher frequencies tend to have 2 or more beams. And so the separation between those is also listed on this table. So if you're interested in observing with the GBT and you want to have just a quick amount of information, that information is included on table 3 on page 10. Okay, so receiver availability. So as I mentioned, the availability of the receivers can vary across different cycles. Typically, across most of the semesters, L-band, S-band, X-band, Mustang, Argest, and KFPA are almost always on the telescope. So most of these are very common in a lot of proposals, and so they tend to drive either the usage for these receivers or, for example, with L-band and S-band, those are physically large receivers, as well as just being very common for H1 observations, and so those tend to be on the telescope 24/7. I also wanted to note that we are in the process of commissioning a new X-band receiver. And so that commissioning is going to be happening over the next few semesters. So keep in mind that we will have a new X-band receiver coming online in the next few years. So as I mentioned, some of the other prime focus, C-band, Q-band, KU-band, KA-band, W-band, can be made available for high-ranking proposals. So again, a lot of the receiver availability is driven by the proposals that are submitted, as well as the ranking of those proposals. And lastly, prime focus 800 megahertz receiver will be available pretty much on a regular basis for the 22A semester as well. And then lastly, just to kind of briefly go over what this image is showing. So this is actually in the in that receiver cabin that I had showed previously, where you have your Gregorian turret. So this is looking underneath the turret. So these receivers would be open to the outside air above this building, but you can see the back end of these different receivers. I believe this looks like this is L-band here, probably S-band over here. And so you have each one of the different receivers fitting into this 8-slot turret, Gregorian turret. And so you will rotate this turret to put different receivers into focus. And so we can have up to 8 available on the telescope at any time. All right, so moving on to backends. So we have multiple different types of backends. The most common one that's used is Vegas. So I will be spending a couple slides after this one discussing the different spectral line mode versus pulsar mode. So I won't get into too much detail with those. We also have the DCR, which is the digital continuum receiver. So that's used for continuum observations. We also have the Caltech continuum backend that is only for KA band. That's usually not used a whole lot. It's not used that often, but we do have the CCB backend available. We also have the Mark 6 VLBA disc recorder. So this receiver is used for VLBI observations that we have with the GBT, and I'll talk about that again at the very end. And then we also have the JPL radar backend. So this is to do any type of radar observations, to study planetary science that I had mentioned in the GBT science slide earlier in this talk. All right, so the Vegas spectral line mode. So the Vegas mode, which you can see we have up to 29 different modes for Vegas. Each one of these different modes basically corresponds to a different bandwidth and spectral resolution. And so for the different modes, depending on what type of science you're doing, depending on what type of frequency you're observing at, can vary which of the spectral modes that you would want to observe. So you would want to check to make sure that if you're targeting a spectral line, that the spectral resolution that you're requesting can actually give you the velocity information that you are interested in getting. So again, these can vary depending on what frequency you're at, but anytime you see something that mentions a Vegas mode, this is what it's talking about. So you can find this on page 14 in the proposer's guide. So this is table 5, where it has a lot of the quick information about all of the different Vegas modes. So you'll notice that you have this kind of break in our Vegas modes where 20 through 29 have this 8 different types of spectral windows. And this is known as subbanding, where basically you can break up your spectral window into having 8 different types of spectral windows that could be focused on different lines. Now with these subbanding modes, you are limited on where you can place the different spectral windows. So they have a note on that. So that's note C, where they mention you have to have this within a certain frequency range in order for it to satisfy these. These ones also tend to have much narrower bandwidths as well. You'll notice that they're typically much smaller than some of the ones that you can get with the lower Vegas modes. So it really just depends on the type of science that you're trying to do for your observations. But anywhere that you see the discussion of Vegas modes, this is what we're talking about. We're talking about the different modes which identify what bandwidth you want to use, the number of channels, which will therefore identify what your spectral resolution is. So that's what a Vegas mode means, is it corresponds to these values. So I wanted to also note that recently all of the modes for the Vegas can now be used for continuum observations. So if you're interested in doing something like this, that you should choose your desired bandwidth and then make a note in the technical justification that the observations will be for continuum measurements. So right now in the PST, there isn't a location where you can identify these as being, like if you select that you're using Vegas mode, let's say 6, but you wanted to use it for continuum, it doesn't give you that option as of right now in the proposal submission tool. But if you do want to use these for continuum and you have your scientific justification written for continuum observations, just add a note about that in your technical justification so that when the GBT staff are going through and checking to make sure that you can do the science that you're proposing to do, that we're aware that you are intending to use this Vegas mode for continuum observations. So it is possible. Just make sure that you make a note about that. All right, there's also the Vegas pulsar modes. So for the Vegas pulsar modes, we have both coherent and incoherent de-dispersion modes available. The bandwidth for the pulsar modes can range from about 100 to 1500 megahertz. And again, with a wide range of channels as well. And so there's a nice table in the proposer's guide where it lists all of the different types of setups that you can do, as well as the polarization types that you can do for these observations as well. So Vegas does have a pulsar mode and a spectral line mode and a continuum mode. So Vegas is usually one of the backends that is most commonly used, except for in rare instances. All right, so GBT observing strategies. So the GBT has a lot of different types of observing strategies. We have multiple instruments, different types of observing modes. And so there's a lot of information or variations in the information on how you can set up your observations. So when you're going through and setting up your proposal or you're setting up your observations, these are kind of some of the steps that you want to walk through. So you want to pick your receiver based on your frequency. So if you're targeting either a spectral line or if you're targeting a specific frequency range, Pick the receiver that satisfies that frequency range that you're wanting to study. Pick your backend based on your observing type. So are you trying to do a spectral line? Are you trying to do continuum? Are you trying to do pulsar observations? Are you trying to do VLBI observations? So you want to pick your backend based on the observing type. And then you want to pick your observing techniques based on your science goals. So the science goals or the observing techniques can vary if you're just doing a point source. If you're just targeting a single point source and all you have to do is just point at that one area of the sky, that type of observing technique is going to be different than if you needed to map a diffuse structure or a large field, or if your lines are narrow versus being broad lines. And so you need to make sure that your observing techniques are based on the science goals of what you're trying to accomplish. And then lastly, calibration strategies based on the receiver and science needs. So what does this mean? So this means that typically as you go to higher frequencies, especially with Argus or with Q-band, so some of the higher frequencies, you need to correct for the dish surface. So I mentioned earlier that the GBT has an active surface, and that's where you have those actuators that can change the dish structure. And so as you go to really high frequencies, you need to do what's known as an auto OOF. And that is where you map the dish structure, you map the dish surface to be able to minimize the RMS levels for the dish surface. And so an auto OOF is something that you would need to do with an Argus observation, but you really don't need to do that with L-band. So your calibration strategies can depend on the receiver and the science case. Alternatively, if you're observing with prime focus, then you don't need to correct for the subreflector or do the focus for the subreflector because you're at prime focus, you're not using a Gregorian receiver, and so you don't have to include that calibration in your observational setup. So that's what I mean by calibration strategies, depending on your receiver and science needs. They can vary depending on that type of information. All right, so different observing modes to derive your reference data. So we have different types of observing strategies. So we have what's known as frequency switching. You might see this acronym as FS or FSW. So anytime you see that pop up, we're talking about frequency switching. You can have this as in band or out of band. And so I'll show you an example of that in the next few slides. We also have what's known as position switching. So position switching is basically where you target your, you point the telescope at your target source and then you point off your target source, and it's the difference between those. So you're switching in position. And then you have what's known as dual beam position switching or nodding. And this is where you nod either between different beams. So at the higher frequencies, I mentioned that a lot of those can have two beams. And so what you would be doing is basically you'd be nodding either the subreflector or the telescope, and it would be moving that signal between your different beams. So anywhere that you see dual beam or nodding, that's what it means, is that you're nodding between different beams in your receiver. All right, so that's just a brief summary of the different types of switching modes that you have. So to go into the background on what each of these are doing. So for frequency switched observations, typically you want to use these if you have a narrow line observations that are relatively clean, that have a relatively clean spectrum. So if you have multiple lines or a large forest of lines, then you probably do not want to do frequency switched observations because you will be getting almost these negative lines in your signal, and that's where you've subtracted your differences in where your line's located. So if you have just a single line, frequency switching might be the best route for you. But if you have either broad lines or maybe a forest of lines, then you might want to go with a different observing technique. But anywhere that you see frequency switch, this is what it means, is that you are switching in frequency and then subtracting those to get your signal. All right, position switched observations. So this is an example of what position switched observations would look like. So you have your figure on the left showing your spectra being on source. So that's your signal from your source plus everything else, background noise, noise from the instrument, noise from the telescope. And then you have your off source, and this is where you point to blank sky, and this is where you're basically picking up everything else that was in your signal as well. And so you can kind of see this little blip down here. So that is actually the signal. So when you take the difference between these and you subtract your off from your on, then you actually can see your signal there. And so you'll notice that it's at 4,500 kilometers per second. So yep, at 45 or so 100 kilometers per second, that's where your signal is located. And so that is what position switched observations are doing, is that you're looking at your source and then you're looking off your source and you're subtracting those two. And that's how you can do the data calibration for those. So I mentioned this earlier. So when would you want to use frequency switch versus position switch? Typically, if you have a narrow line, so anything that's less than about 100 or so kilometers per second, that's in a non-crowded spectrum, then you probably would want to use frequency switched observations. If you have a narrow line, but it's in a crowded spectral region, or if you have significant RFI or strong RFI, then you might want to do position switching observations. Or if you just have like a very broad line, then you might want to do position switched observations as well. All right, so observing modes for different sources. So first I'm going to cover small sources. In the next slide, I'll cover about large sources. So if you have a small source, so if your source is less than what your beam size is, you're doing, let's say, line observations, and you're doing position switched observations. So for these, you can either nod between two beams if you're not limited by baselines, so baselines between the different beams. You could do a sub-beam nodding. Typically, this is done if you're doing KA, Q, or Argus. And if you're doing K-band or W-band, then you might want to use nodding. You can do what's known as an on-off. So on-off is position switched, simply just position switched in your scripts. You would identify it as being an on-off. And then you can do what's known as tracking. So tracking is where you are basically just pointed directly at your source. So you're doing some amount of integration where you're looking at your source, and then you would almost have to track a position that's off your source. So it's essentially doing almost the same thing as on-off, but you would have to actually give it an offset of where you would want to point and track as well. So if you're doing line observations, but you wanted to do frequency switched, then you can just use your track scan. You don't need to be pointing off because it's frequency switching as it's observing. So you don't need to have an off position for those. You can just simply track on your source, and it will account for that in the background. And then lastly, if you're doing a compact source with continuum observations, then you might want to do what's known as a daisy map. Typically, you would think that if you have a relatively compact source, that you wouldn't need to do any type of mapping, but we found that daisy mapping, and I'll show that in the mapping discussion, what those look like, but daisy mapping is actually an efficient way to deal with the 1/f noise that you can get in doing either high bandwidth or long integration continual observations. All right, so for large sources, so if you have extended sources, then you almost entirely would want to do some type of mapping. And I will cover the different types of mapping in the mapping talk at 4, but just to kind of briefly go over if you have a very, very large map and it's much larger than what the field of view is for your receiver, then you will want to be doing what's known as an RA long map or a deck lap map. And when we do the mapping calculator, I'll show you where those acronyms pop up. If your map is roughly about the size of your field of view for your receiver, then you might want to do, you have a few different options that you could use for those types of mapping observations. You could do an RA long map, deck lap map, but there will be significant overheads for your turnaround. So basically, if you're just going up like a couple beams and then you're turning around, you're constantly moving the telescope up and down pretty quickly, or you could be moving up and down pretty quickly. So there could be significant overheads just in that turnaround time. There's also what's known as a daisy map. So a daisy map, as I mentioned earlier, is mainly if you are interested in your central point source or your central source. And I'll talk about those again in more detail in the mapping talk, as well as just a point map, which is basically a grid if you need a very deep spectrum on single parts where you point at a region and then you move over to a different spot and you point for a region and you move on to a different spot. Typically, the RA long maps and the deck lap maps are what's known as being on the fly mapping, and that's where you're constantly moving and taking data as the telescope maps around your area, versus a point map where you sit on a specific area or region of the sky for a bit longer. Okay, so overhead estimates. So one thing that you will want to keep in mind when submitting your observations is that all of your observations will need to have overhead estimates included. So when you submit your observations, you don't want to just put in, okay, I need this amount of time on source. You will want to have thought through the amount of overhead time that you need as well. So one of the things that you will need to include will be point and focusing. So if you are if you're just doing fine focus observations, then all you need to do mainly is correcting for pointing. If you're doing Gregorian observations with any of the Gregorian receivers, then you will need to do a point and focus because you need to focus the subreflector. Typically, these are done roughly every 30 minutes to an hour, depending on the frequency and the time of day. So it can vary depending on if you're doing daytime observing versus nighttime observing. And typically the point and focus scans take about 5 minutes. It does 4 pointing scans and then 1 focus scan. Each one's about a minute, so it takes roughly about 5 minutes of overhead each time you do this. You want to include that if you have, let's say, for example, a 5-hour observing block or 6-hour observing block, and you do this once every hour, then you will need to account an extra 30 minutes of overhead just for doing a point and focus scan. I had mentioned earlier about the auto OOF. So that is just to do OOF corrections if you're doing high frequency. Typically daytime changes are about less than an hour on time scales. And so usually the OOF can do more harm than good if you're trying to do these in the daytime as of right now. We are currently trying to incorporate an instrument on the telescope that's called LASSI that will be able to improve and allow for daytime observing. But right now, typically if you're doing an OOF, those will usually be during the nighttime observations. All right, I'm gonna pick things up a little bit. So about the proposal call, so the deadline is Monday, August 2nd at 5 p.m. There's a link for the proposal call. Disposition letters for the proposal call will be sent out in early November, with the observations set to begin February 1st, 2022. There will be an observer training school. So say, for example, your proposal is accepted and you're not sure how to observe with the GBT or do data reduction with the GBT. There is a training school that will be held late January, early February, and there's a link for that down here. Joint proposals. So we do offer joint proposals with all of the instruments that's listed here, as well as the VLA. So this information, I won't go into the details, but the information is listed in section 2.2 of the proposer's guide. So if you're planning on submitting a joint proposal, if you're interested in submitting a joint proposal, please view those, and it will have all of these links there as well. So if you're interested in doing a joint proposal with, say, for example, Sophia, this link will take you to any types of information that you would need for those as well. All right, the differences between your proposal categories. So regular and large proposals. So regular are offered every proposal cycle. Large proposals are only accepted in the February deadline. So we used to have them available every cycle. We have since changed that. And so now they're only being accepted in the February deadline. So we will not be accepting any large proposals for this current cycle. The differences between them are either the amount of hours or how long your observations will be taking place. So that's the main difference. These are also listed in the proposer's guide as well. If you would like a link for that or the section for that, let us know and we can put that in the chat as well. We also have triggered proposals. So these are submitted during the normal proposal deadline. So it's be the August 2nd deadline. And they are intended for pre-planned observations of transients, so whose times are not well known. So if you had, let's say, for example, you wanted to target FRBs and you're not really sure where these FRBs will be located, when they'll be located, you can still submit a proposal for those and just list what the triggering criteria is. So that is one of the things that you really need to make sure that you have listed if you're submitting a triggered proposal, is that your criteria is clear and well justified. Lastly, there's also the director's discretionary time. So typically these are for target of opportunity. Let's see, I think I was on a DDT a few semesters back when we had a comet that was passing through, and we wanted to observe that one. So it was an unaccepted phenomena. And so we submitted a DBT to observe the chemical composition for those. So that would be an example of a target of opportunity, is if it's an unexpected phenomena and you need a really rapid response. There's also exploratory time. So if you wanted to have a proof of concept or proof that your observing strategy or setup can get you the science that you want, then you can propose for just a few hours, target a pilot study, just to prove that you can be able to get the science that you're interested in, and then submit a proposal showing those results or showing that proof of concept in the next proposal cycle. So director's discretionary time can be submitted at any time. It does not have to be at the proposal call. We also have a connection with the VLBA. So you can have the GBT in with VLBA observations, which will help improve the sensitivity of those observations. So as I mentioned, we use the Mark 6 VLBA disk recorder to do those observations. If you're planning on submitting an observation for VLBA plus GBT, you need to make sure that you include all overhead estimates in your technical justification and as well as in your setup. So if you want to have your observations start at, say, 12 a.m., you need to make sure that you include an extra hour or so ahead of time for the operator to be able to have the time to set up the observations, to do any type of pointing, to do any type of calibration that needs to be done. So make sure that you include those overhead estimates in your time estimates. And there's more information that can be found on the link at the bottom. So observations data reduction, successful proposals will be observed by the PI or another member of the PI team. So you will be doing the observations yourself. Now we do have training schools that are offered 3 times a year for observers to learn how to control the telescope and perform data reduction. So typically these are held either in January, February, May, and September. So the next one coming up is in September. And there should be a link in the Observer Training School link that I shared earlier, where if you're interested in signing up for that or attending those links are available as well. Lastly, I'm going to mention that there is the GBT data reduction pipeline. It was created by Jim Bratz and Joe Masters, and there's a user guide on working with the pipeline. Typically, the pipeline data reduction is if you're doing mapping. So you usually don't need to do this if you're doing single pointing observations, but if you're mapping, then you might want to take advantage of the data reduction pipeline to help process some of your data. All right, so I will stop there, and I think we're at 3. And so I think we will pause for a minute and then move on to the PST.
Does anybody want to ask Natalie a question? If so, raise your hand and we'll give you the ability to speak. There were a couple questions that came in during the talk. The link to the call to proposals was put in the chat, as well as a link to the help desk if you have questions. Yeah, something just came into the Q&A. Will the pipeline work on archival data? Yes, is the answer to that. But you need to, the pipeline works on SD-FITS file, and currently the archive returns the raw data file. So you have to run a little software tool to put it into SD-FITS.
Great. Okay, well, feel free to continuing to post questions in the chat or the Q&A box. Again, we will have discussion time at the end to address any other questions that come up. But keeping on schedule, I'm going to move on to the next talk in our series, so the PST. So the PST is going to be a part slide, part demo presentation. So we'll cover a couple slides, and then we will move on to a live demonstration at the very end. Okay, so now the PST. All right, so all proposals for the GBT are submitted through an online website that's known as the Proposal Submission Tool. So you can access this through the my.nrao.edu link, and then navigate over to the proposal list, or you could just type in the link here if you're already logged in. So the PST is used to submit proposals for the GBT, VLA, VLBA, and GMVA. However, much of the information that you will be adding can vary depending on the different telescopes that you've selected. So if you're submitting a GBT proposal for the first time, you've submitted a VLA proposal in the past, a lot of it will look very similar. A lot of the sections will look very similar, but there are some slight variations because we are a different instrument. So just be aware of that. All right, so when you're trying to log into the PST, as I mentioned, you want to log in doing the my.nrao.edu, and it will bring you to your dashboard. Then you want to click on the Proposals tab. So that's the tab, the second one that's over, and that'll bring you to a page that looks like this. This will basically just summarize all of the proposals that you've submitted in the past, ones that were both accepted versus not accepted versus ones that were still drafts. And so it's just kind of a summary of all of the proposals that you've created in the PST. Now, if you wanted to submit a new proposal or create a new proposal, you want to click on this tab over here that says New Proposal. All right, so once you click on that, it brings you to a page that looks like this. And so, as I mentioned, you have a lot of different options for different telescopes through the PST. So for us, since we're doing a example for the GBT, you would want to click on the picture that has the GBT. And then once you've clicked on that, it will bring you to a draft template for your proposal. So the draft template will look something like this. You have different options to validate. And so once you validate, it will tell you if you've run into any issues or forgotten to fill in any information in your proposal. You can print your proposal or export it as a PDF. And then you can submit it by clicking the submit button up here. Through all of these different sections, and I'll get to them in a minute, you can edit any one of those sections by clicking on it, and then clicking the edit button. And that should allow you to edit those sections as well. Okay, so now going through the different parts of a GBT proposal. So you'll have your general information. So that's basically this first page right here. The information that goes in there is your title, your abstract, the proposal type, the scientific category, your observing type, and then it will ask you if it's a joint proposal with one of the other proposals or instruments that were listed previously. Then you have the authors tab. So this is where you add authors officially to the proposal. So any authors that are officially on the proposal must be registered users. So if they aren't a registered user and they want to be officially on the proposal, you need to ask your team member to officially sign up on the my.nreo.edu account in order to add them as an author on the proposal. Then you will be uploading your scientific justification. For regular proposals, these need to be 4 pages or less. If it's a large proposal, which again, we aren't offering large proposals for the August deadlines, but if you would like to submit a large proposal for the February deadline, those can be up to 10 pages. Then the next tab is the technical justification. So there's 9 different technical questions that need to be addressed, and I will go over those when we get to that section. You'll have your sources tab. That's where you list your target source information, basically where you want to point the telescope. Then you have your resources tab, and that's where you're going to be setting up your backend information. So like what type of receiver you want to use, what type of Vegas mode you want to be using, bandwidth, all of that type of information, where you want your different spectral windows to be centered. All of that information goes into your resources. Lastly, you have sessions. And this is where you basically set up your observing sessions. And so we'll be pulling information from your sources and resources. So I would recommend that you finalize your sources and resources information first before you try setting up your sessions, because it will be pulling information from those sections as well. Okay, so now we will continue on to the live demo. So if you go to the my.nreo.edu page, so you would get something that looks like this. So then you would log in. Okay, and then it will bring you just to your basic dashboard. You'd want to click on proposals. So you can click on proposals. All right, and then we're going to just go ahead and make a new proposal for this demo. And we're going to click on the GBT, and then we're going to click create. And so this is how you can create a new proposal. All right, so now let's go and start putting in just some basic information. One thing I want to point out, since I've noticed this before in the past, if you end up editing or trying to edit something and then just want to either save it the way it is, it will throw an error about the abstract. And so just make sure if you do see that error, it does not like that it's left being blank. So you have to just put something in there if you're just trying to save what you have. Okay, so just wanted to let you guys know that to be aware of that. All right, so let's put something in. Then you have your different proposal type. We'll just put it down as regular. It's not a sponsored proposal. So sponsored is if you're sponsored by one of the different, I guess, groups that we have on site. So I had mentioned Nanograv earlier. There's also a large group of other types of sponsors that we have. This is not a sponsored proposal since it's not being submitted through any of those. You have your scientific categories. So we'll just put it there. And then I'll just leave abstract the way it is. This isn't a joint proposal, so I'm going to leave this blank, but you can see where you can select a different joint proposal. And then you have your observing type. So for this one, we'll just say that we're doing, maybe we'll do spectroscopy, and maybe we'll do on-the-fly mapping. Okay, so we'll do that, and then we'll save it. And then it's going to update it with that information. Okay, so that's what you will do under the general tab. It's basically just a summary of your proposal. Okay, authors. All right, so authors. So this is where you can add different authors to the proposal. So let's see, I think Dave is the search. Dave Breyer. Oh, so I'm going to add Dave just to the template. Okay, so that's how you can add someone to the proposal. You can search for their name by typing in either their name or their email, and then click on the author that you would like to add. And again, if you need to change the PI, once you've added someone in there, you can change your PI, you can change the contact information, but all official authors on the proposal will be added here. And if their name isn't listed, then you will want to ensure that they are registered users, because that could be why that they aren't listed if you search for them and you can't find them. Okay, so that's what that does. And then let's see, science justification. So this is where you will be uploading your science justification. It needs to be in a PDF or TXT format. Your font size needs to be no less than 10 points. And again, no larger than 4 pages. And this is including figures, tables, references, all of that information. All right, so for this, I have created, let's see, 2 different examples. So for this one actually has 5 pages. So this is over the 4-page limit, but I just want to show you what it looks like if you try to upload something that is doesn't satisfy that limit, just so you can see what that will look like. All right, so we will upload this one. Okay, yep. So there's the 5 pages. This is what it looks like. And you'll notice that you see that it gives you that in red, letting you know that you've added a document that's over the 5-page limit. All right, so let's say you needed to go back and change that. So you can click replace. It brings you that option again. So now let's click on the one that's 4 pages. And that, and then we'll do upload. All right. And then once that one uploads, you'll notice that this error message will disappear. There we go. Okay. All right, so your science justification will be done or written in either an outside program. I tend to use LaTeX to write a lot of my documents, but you could use Microsoft Word and then export it as a PDF. But yes, it does need to either be in a PDF or TXT format to upload your science justification. All right, so next, your technical justification. And one of the things that I wanted to mention about your technical justification is that while your science justification is limited to 4 pages, your technical justification has no limits. And so we recommend people include as much information as possible. So for example, the sensitivity calculator, mapping calculator that we will get to a bit later, we recommend that you upload those results or those calculations, you copy and paste the results that it gives you directly into your technical justification. So as a GBT postdoc or the support scientist, we read through your technical justifications and attempt to recreate the observations that you are proposing to do. So the more information that you give us, the easier it is for us to recreate or attempt to recreate the proposals or the science observations that you're attempting to do. One of the things that you want to make sure that you keep in mind is that you are consistent across your technical justification. So in the past, I have seen proposals that come through where someone has decided to change their observations, I guess when they were writing the proposal. And so what they used to create their sensitivity calculator, maybe they used mode 3, whereas when they ended up doing their resources setup, they're actually using mode 6. So you want to make sure that when you're creating your proposal, that a lot of the information that you're including is consistent across all of the different parts of your proposal. And so the best way to do that is to ensure that you give us as much information as possible. All right, so going through these, most of them are relatively straightforward. Like it will ask you if it's a joint proposal. You know, for this one, we can say it's not a joint proposal. You know, if it's a pulsar observation, then you would need to include that information. This isn't a pulsar observation, so we'll just do NA for those. So it also wants you to include information about if you're doing fixed time observations or anything like that. It wants you to kind of cover what you use to make your sensitivity calculator. Like, are you wanting to do frequency switching versus position switching? What type of bandwidth did you need? What type of spectral resolution did you need? Basically, you need to justify that type of information and the observing mode that you're using for your observation. So maybe you're using position switching, and so you would want to say, okay, we're using position switching because we're targeting broad lines. Or maybe we're doing you know, position switching because we have a crowded spectrum or we have multiple lines. And so we're using position switching to reduce, you know, reduce that. Or, you know, about your spectral resolution, that we needed to have a specific number of channels across a line. Therefore, we need this type of spectral resolution to be able to get our science. So that is pretty much what this section is talking about, is justifying the inputs as well as all of the values that you used to make those calculations. So if you're using the sensitivity calculator, you know, you would want to include those results since it can make it easier for us to be able to recreate the sensitivity values that you're using in your proposal. Same thing goes with the mapping calculator. So that's this next section down here. So the mapping calculator, you put in the results from either the sensitivity calculator as well as a lot of additional information about the frequency, source, map size, a lot of that types of information, and then just justify those values as well. This next section down here, let's see, that one talks about RFI. So if you're in the higher part of the spectrum with, say, for example, if you're up at 3 millimeters with Argus, then you really don't have to worry about RFI. But if you're at some of the lower frequencies, then you need to talk about how you will be handling RFI or potential RFI in your observations. This next one down is talking about overhead. So your overhead, you will want to include estimates on, you know, if we're doing a 5-hour observing run, then we're going to need to have, you know, maybe 5 chunks where we are doing our auto peak focus. So we're adding in 5 minutes or roughly 30 minutes for those. So you'll want to include that. It's basically where you say, okay, this is all of the different types of overhead that we are considering, you know, slew time, receiver changes, pointing focus, auto oof, maybe an additional calibrator observation, changing between receivers, all that type of stuff. You will want to include that overhead in this section here. And I found that it's easier, at least for me, if I break it up into what each of my different observing blocks are and then how much overhead I need for each one of those. So that way when I create my sessions later on, I just know that, okay, I have, I've already gone through and estimated how much overhead I need for my 3-hour observing block, and it can make creating your sessions a little bit easier, at least in my opinion. All right, so we went over the joint proposals. This next one about either novel observing or data reduction techniques. If you're a new observer, you probably will not be doing anything that's a new type of observing session, but if you have a new technique that you wanted to try out or style or something like that, and you're unsure of what type of information to include on this, please reach out to the scientific staff. That's why we're here. We can help walk you through either the type of setup that you're trying to do. And we'd much rather help you before you submit your proposal than to try and reason our way through it once we see it as on the receiving end of the technical tack. Lastly, okay, so let's see, then you have your minimum and maximum LST time. So this is only if you are observing at a different session than what was generated when you set up your observing session. So for these, I guess I've never really needed to do something like this. Most of the time when I've set up my observations, it automatically generates it. But if for whatever reason you need to observe at a different minimum or maximum LST time from the calculated value, you'll need to justify those results here. All right, so that's kind of an overview of the technical justification. Oops, so I'll just save that. Okay. Next one down is sources. And so this is where you can, let's say you're resubmitting an observation, you can copy sources from a previous proposal, or you can just create a new source group. So for this demonstration, I'm just going to do a new source group. We're going to call this sources, and then we'll do save. Okay, and then now we're going to add a new source, and we'll do, let's just search for one. So you can search a database if you know what the name of your source is, or if it's a well-known source. And so for this one, I'm just going to search for the supermassive black hole at the center of the galaxy. And so you can do search, and then it will automatically generate a lot of that information. Okay, so we will save that. Okay, and so now it's created that source for us. All right, so that is how you can add sources, or you could just go through and just add a source. If it doesn't show up in Net or Sinbad, you can just create your own source. And then you will just need to make sure that you pass it all of that information. Okay, so we'll cancel that for now. Okay, and then we'll move on to resources. So resources, as I said, is where you do your, you set up your backend information. And so you want to do new resource group. And so we'll just call this ammonia. Okay, and then we will need to add our resources. All right, so then you'll see a page that looks something like this. Okay, so now we'll just call this NH3. You can select which band you want or which receiver you want. So we'll do KFPA since that's what ammonia is in. You can change the different backends that you're using. So for this one, we'll just keep it simple. We'll go with Vegas. It's a spectral line mode. And so we'll do 7 + 1. And so that's where we can use all 8 spectrometers. And so then here is where you will be selecting what the Vegas mode is. So I mentioned earlier that the Vegas modes will come up when you're doing your sensitivity, mapping calculator, and PST. So you can select different observing modes based on those different parameters. So you'll notice that as you select a different observing mode, it's going to automatically change with the bandwidth and what the spectral resolution is. Now, one thing that I want to make sure that you all are aware of, just to save you a little bit of headache, is that, let's say, for example, we wanted to put in, let's say the lower frequency ammonia line, we'll put one there, and then I think the next one's like something like that. If after you've added in your rest frequencies, which you have to do here, if you change what mode you're using, it will erase all of your rest frequency information. So now let's see if I go to mode 3, it clears that. So just make sure that you are happy with the mode you're using before you start adding in some of your rest frequency information, because otherwise, if you change it after the fact, it will clear those slots as well. Okay, so just be aware that you want to be happy with your Vegas mode before you start adding in some of that extra information, just to save yourself a little bit of headache. Okay, so we'll just put 694. I'm just going to use, hopefully it's not going to freak out if I put all 4. Yeah, and then we will just change some of these just to fill this in so I can save this. Okay, so we'll save that. All right, so then it saved all of that information. And if you want to see that information, you just click this drop down and there you go. It saved all of your different spectral setups. Okay, so that's how you can go through and create resources. You also have sessions. So again, as I mentioned, when you go through and create your sessions, it's pulling information from both your sources and your resources. So we'll just call this session 1. And let's see, so we'll do, yep, sources. If you had different sources or different source groups, like say, for example, you're targeting different, maybe different massive star forming regions that are across the galaxy, then you might want to have different groups where those, group different types of clusters together or something. You might want to have different source groups. And so if you had multiple source groups, you could select those different ones. Since I only had one that I created, it only gives me one option. Same thing with this. If you had different resources, you would need to put those different resources. And then lastly, your time. So the amount of time that you need per session. So this is when I was going and talking about in your technical justification about your overhead, that I find, at least for me, that it's easier to break up or to think about my observations almost in these different types of observing sessions where I say, okay, I want to break up my observations maybe into 2-hour observing blocks. And so the amount of overhead that I would need for those, as well as the amount of time on source, will help me understand how much overhead I would need for each of those different sessions. But the value that you plug in here is the amount of time that you need, including overhead, time on source, time off source if you're doing either mapping or position switching. All of that information goes into a single observing time. So we'll say that, okay, we want to do 2 hours for each observing block that we have, but maybe we need a total of, let's say 6 hours on telescope time to be able to get those, to be able to achieve the science that we want. And so for that, we would change this value to 3. And so we would have essentially 6 hours that we're requesting. That's going to be spread up across 3 different observing sessions, with each session taking 2 hours of time. So reasons why you might want to break up your observing session from doing maybe 2-hour blocks instead of 6-hour blocks would be one, that it's easier to schedule if they're smaller blocks. 2, that it might be easier or dependent on the amount of time above the horizon that your source is up. So, if it's a low declination source, maybe it's only above the horizon for 4 hours, but you need 6 hours on source. And so that's why you would want to break up your observing runs into different sessions. And so this value here is the amount of time that you want per session. And then you would just multiply that by the number of sessions that you would need. So then you would want to save this. So usually if I do the calculate min max, it doesn't change that. Normally what I have to do is I usually save, and then I go back into session, and then I do edit, and then I do calculate, and then it updates it. So if it doesn't update the first time, it might mean that you need to save it, or it needs to know what type of source group that you're doing. And then you just need to go in, edit, and then calculate it. Okay, so we'll save that now. So now if we go back to our general section, you'll notice that the total time up here is 6 hours. So one thing that I do want to make a note of is that all of the observing blocks are scheduled in 15-minute or quarter-hour increments. So you want to make sure that when you are scheduling your scheduling blocks, or you're setting up your observations, that you make sure that you set these up to be in quarter increments. So it doesn't really happen too often, but usually about once or so every cycle, we do see someone who will ask for 6.13 hours on source, but the telescope is always scheduled in quarter increments. And so you want to make sure that when you're setting up your observations, that you set them up to be in quarter increments. All right, so I think that covers most of the demo. We are at 3:30 now, so I think I will just show you what it looks like to validate. There will be a few issues with it, but you will want to make sure that you check your observations and that you fix any type of issues that come up. So one, yes, the proposal abstract was too small. It was just a single word. The rest of these are showing up as being issues where I left certain parts of the technical justification blank. So now let's see if I do NA. I'll just copy this for all of them. Again, you would want to fill in this information and not do what I'm doing right now, but just for example purposes, and just to get this to validate so you can see what it looks like when you actually validate an observation. I'm going to fix these issues. Awesome. And we'll save that. Okay, so now let's try validating again, and we'll see. Oh, I guess it's still too small. So let's go back and we'll change that. Okay, and should be. Okay, we'll save that, and hopefully that passes. Yes, so we'll validate. Okay, well, yeah, so usually once you actually type in your abstract, you shouldn't be getting that error. I'm not sure how to get this. Let's see, maybe if I just do this a couple times. Just want to make sure that it validates so you can see what that looks like. There we go. All right, so if everything validates fine and you don't have any missing values or any blank text boxes, this is what you will see. Again, it doesn't check to make sure that you are consistent across your proposal and that you have used the right Vegas mode for both your sensitivity calculation, mapping calculation, and in your resources section. So it doesn't check for any of that type of stuff, but it does check to make sure that you haven't forgotten to fill in one of the text boxes in your technical justification. So that's kind of a nice way that you can validate things. Okay, so I will stop here for these. I guess we can check and see if there were any additional questions that popped up, or if there was any questions on setting up with the PST. We can briefly go over those now. Otherwise, we can move on to the sensitivity calculator.
There was one question right at the end asking if you could withdraw a proposal and resubmit it.
Yes, you can withdraw a proposal and resubmit it. I myself have done that in the past a couple times. I think the closer you get to the deadline, the more you might run into issues with a lot of people submitting.
Yes.
So you might want to be careful about retracting it. If you might run into internet issues, but yes, it is possible to submit and withdraw and resubmit a proposal.
There is a bug in the PST that doesn't allow withdrawal within the last 10 minutes before the proposal deadline. And so if you need to do one, then you need to submit a help desk ticket. But before that time, it's possible to withdraw it and resubmit it.
It's safer just to copy it, make the update, submit a new one. Make sure that works first before you withdraw the old one. Because we'll figure it out if there's two of the same proposals submitted.
Okay, any other questions? Okay, so we'll move on to the sensitivity calculator. So let me close this one. Okay, sensitivity calculator. So similar to the PST, we will be doing a couple brief slides, and then I'll be going over a live demo. Okay. All right, so the sensitivity calculator. So this is a user-friendly way of helping observers to estimate their time on source. And so any of the generated results from the sensitivity calculator should be added to the technical justification of the proposal. So I had mentioned this when we went over those different sections, that when you do your results, that you will want to add those to the technical justification blocks about the time on source that you need. So accessing the sensitivity calculator in the PST on that box, it does give you a link to the sensitivity calculator, but if you're just trying to navigate there, we do have, that's what this link is. It's just a link to the sensitivity calculator. There also is documentation for the sensitivity calculator. So if you're working through it and you have questions, if you're unsure of what a specific parameter is, we do have documentation on the sensitivity calculator, which can be found here. All right, so for the information that you need for the sensitivity calculator, so there's 4 different kind of sections of the sensitivity calculator. So the first one is general information, and this is pretty much where you identify your desired sensitivity. And you want to confirm the units that you'll be using for your sensitivity. So there's different types of units that you could be using. You could be trying to calculate your sensitivity for flux density versus the antenna temperature versus the radiation temperature. And I'll be going through what the differences are between those in the next slide. You'll also need to pass it the hardware information. So this is where you tell it what type of backend you're using, receiver, the bandwidth, the switching mode, so position switching, frequency switching, etc. So all of that type of hardware information will be added to the sensitivity calculator. You will also need to pass it information on the source information. So this is where the frequency of either the spectral line that you're trying to target, potential Doppler corrections, velocity, as well as background contributions. So if you have, other either emission or other contributions that could be contributing to the sensitivity estimates, that's where that information goes in, as well as elevation limits, etc. And then lastly is going to be information on the data reduction information. And so this would be any type of averaging. So if you're doing multiple polarizations, for example, and you plan on averaging those multiple polarizations, or if you plan on smoothing, multiple channels, or having a higher velocity or frequency resolution, all of that information will be included in the data reduction section. All right, so as I mentioned, you have different types of units that you'll be using for the desired sensitivity. The first is the flux density. And so this is in millijanskeys. And so this is as if you were measuring it from above the Earth's atmosphere. And this is the default. So once you open up a blank, sensitivity calculation, it will default to flux density. You also have the option of selecting the antenna temperature. And so this would be as if you were measuring it from below the Earth's atmosphere. You have the radiation temperature, which is as if measured from above the Earth's atmosphere and defined for any sources of any size. Your main beam temperature is similar to the radiation temperature, but it's defined for sources whose diameter extends to the first nulls of the telescope's beam. So if you extended sources, then you might want to use this one. And then lastly, you have the forward antenna temperature. So this was actually a new option that was recently added. So it's the measured antenna power in the forward on-sky direction corrected for atmosphere. And so this is mainly used for Argus observations. So that's why it was recently added, was once we installed Argus and had Argus available, we ended up adding in this option as well. So all of these temperatures are going to be measured in millikelvin, whereas the flux density is measured in millijanskys. But that's just a brief definition of what each of these, or what the differences are between them. But if you're unsure, or if you're going through the sensitivity calculator and you're not sure which one to use, I would recommend looking also at the documentation. They do go into a lot more detail about what each of these different values are, but just when you see them in the sensitivity calculator, that's what the difference is. Brief description of what the differences are. All right, so accessing the sensitivity calculator, I posted the link earlier. Once you log in, this is basically what you would end up seeing is a page that looks like this. And if you do get stuck, the user's guide or the documentation can be accessed by clicking this one, but just be aware that it will navigate you to a different page. So you might lose some of the information that's in there. So just be aware of that the option is there, but you might want to make sure that you open it maybe in a different tab if you're currently walking through this while creating your proposal. Okay, so now we will go back to the website. So we will do a live demonstration. Okay, so this is basically once you open up a fresh page, this is what it will look like. And again, you can click on that and it will take you to the user's guide, all of the information about the different types of values, hardware, software, source, data reduction, observing time, all of those, that information can be found in the user's guide as well. Okay, so general information, as I mentioned, you have your different sensitivity units. And then you can either have it set to derive your observing time from a desired sensitivity, or you can have a sensitivity from a set of observing time. Typically, for your observations, you will almost always want to use the first one, especially if you're trying to get down to a specific sensitivity for a spectral line or a source, then you will want to derive the amount of time on source that you need in order to get that sensitivity. So you probably will want to go with the default. And then let's say that we want to do a sensitivity of maybe about 10. Maybe we'll do 1. Okay, so you put in what your desired sensitivity is. And then you can select what type of backend that you want. So we'll just go with Vegas since that's what we set up in the PST. So you can select the different receivers. So we'll do KFPA, which is what we used last time. For this one, you can select what your different beams are. So we'll just do 7. And we'll just do dual polarization. And then maybe we'll just do narrow bandwidth. Number of spectral windows. So we'll just stick with 1. And then I might want to do position switching for these observations, since ammonia can have a hydrophile structure. All right, so that's what the hardware information is it will basically walk you through those different steps. Now I do want to just show you what happens if you do decide to change something. So let's say, for example, we wanted to also measure OH or maybe H2CO, formaldehyde. If you change your receiver, it can affect some of the other parameters as well. So since C-band doesn't have multiple beams, you'll notice that that ends up getting defaulted to 1. So each one of these different drop-down menus can vary depending on what you've selected above that. All right, so let's go back to KPI. Okay, we'll just go back to 7. Okay. So next, source information. So this is where you put in what your frequency is. So for this one, we'll say we'll look at the ammonia 1,1 line, which is located at this one. And again, this is in megahertz. So we'll say that our Doppler correction, let's do radio, and you can pass it your velocity. But if you're doing, let's say, for example, high redshift or high redshift observation, you can also pass that along as well. So you do have the option of changing that to do redshift if you are doing redshift observations or extragalactic observations. All right, so okay, go back to this. All right, so then you can change what your source diameter is. So if you know what your source is, so we'll say that our source, we'll say maybe is about half an hour per minute. We'll say it's 30 seconds or so. Okay, so you can select that. And then you can also select what the source contribution corrections are. So if you know what the background contributions are that could be affecting what your sensitivity is, you can add that. But if you're looking at a source that's in the plane of the Milky Way galaxy, you can select the internal galactic model, and then you can just pass it the approximate right ascension, and it will estimate what the background or what the contributions are from the Milky Way there. So for me, I study a lot of stuff in the galactic center. So that has roughly about 17 hours right ascension. So we'll just put that down. And it has a declination of -28 or so. So we'll change source declination to that. And then minimum elevation, since we are doing somewhat of a higher frequency, again, we want to make sure that our minimum elevation is higher. And so you can select that. We'll just put it at 15 for now. Okay, lastly, you have the option of doing different types of data reduction. Typically, I normally just leave those as the default at 1. Roughly half the time I spent on source is what I would spend off source, especially if you're doing either point source or if you're doing position switching where you're looking on and off, or if you're doing frequency switching where basically you're spending the same amount of time one versus the other. Then you can select those here. I mentioned also the ability to do some averaging. So if you're going to be averaging multiple polarizations, you can select that or deselect that. And the same thing with doing your difference for your signal versus your reference observations as well. Lastly, this very last box down here is where you select what your velocity resolution is. So for us, I will just leave it as 1 kilometer per second, but you can always change it to whatever type of velocity or frequency resolution that you need. So if you change it, let's say right now it's in velocity. So if you wanted to change it to frequency, it has you, you can add that information in megahertz. I'm going to leave it in velocity since I'm most familiar with that. Okay, so now once you've added all of your information that you want to click this button here that says update results. And so that is where it goes through and calculates how much time you need on source. Now we've got a lot of time on source. So I think that's probably because I did this. So we'll just keep it at 1. And then you can update results, and you'll notice that it changes the amount of time that you need on source. Okay, that's still very, very high. I think it's probably because of what I had for my desired sensitivity. So maybe we can get away with doing 10 millijanskis. So I'll do that. Okay, and those are the new results. And again, when you're actually going through and doing your calculations, you want the parameters that you're choosing to be driven by the science. So you don't want to be changing your sensitivity values if you're concerned about having a very high observing time. Don't just change your sensitivity by an order of magnitude if you're nervous about asking for a few, a dozen hours or something on source. You want to make sure that your sensitivity calculation supports the science that you're aiming to do. So if it's high and that is what you need to get your observations or get the science that you need to address your science questions, then that's what you need. So that you can make, a few changes if you need to, or tweak a few things where maybe, for galactic center source, lines are typically 10 kilometers per second. So maybe, 1 kilometer per second is fine. And maybe I could go even up to 2 or 3. So, making adjustments, with those reasonings are fine, but you don't want to just be changing your parameters in order to get the smallest amount of time, because we do go through and we check, your technical justification. We check the values that you are including to make sure that you are able to get the science that you're aiming to do in your science justification. All right, so just be aware of that. But if you do make any changes, make sure that you update your results, and you can see how some of those vary. We'll put this maybe back down at 1. Maybe we'll do 5. Okay, something like that. Once you are happy with your results, you can click Save to File. Usually this will end up, saving something where it gives you all of this types of information. So it basically has all of the different parameters that you use to go through and do your calculations, as well as the results. And so this is what we are, if you have a chance to add to your technical justification, we recommend that you just copy and paste this. So I'm just going to do this. And then let's see, let's go back to here with our proposal setup. And then you will want to say, like that. And then you can go through and add that. So when we go through and try and calculate how you got, your value of, maybe 460 seconds on source, we know exactly all of the parameters that you use to put that in. And again, you're not limited by the number of pages for your technical justification. So we really highly recommend that you include your sensitivity calculation from the calculator in your proposal. Okay, so you can view your results that way, or you can view your results here, or you can change them to a grid. So whatever makes it easier for you to kind of see the different values that you've been including. But that is just kind of a brief overview of the sensitivity calculator. If anyone has any questions or would like to see any type of other examples, we do have some time where I can go through and either make those changes or make those adjustments and show you what those look like.
So we had one question. Under what situations would you enter forward antenna temperature instead of antenna temperature?
Yes, so forward antenna temperature, you would want to use that if you were doing Argus observations. So if you're doing Argus observations, you would want to select forward antenna temperature and then, and then click on this, and then we will go down to the Argus observations, and then you can add those in there as well. But yes, the forward antenna temperature is the newest option under the sensitivity units, and that was added for Argus specifically. All right, any other questions?
I think all the other ones have been answered. Oh, there's one that just came in. If we need different sensitivities for different sources, should we add all together in one box in the justification page?
Yeah, I would say it wouldn't hurt to include those different sensitivities. If you have the same setup, like the same resources set up, where the only thing that you're changing is your sources, then I would say you probably are fine with just one. The only thing might be if you have, I guess, large changes, like if you have like multiple different ranges in your declination. So like if you're looking at something that's low declination versus high declination. So let me actually make that change now. So let's say we're going from -28, we'll do maybe 60 or something. So those, I think I actually changed other things. Okay, so going from 64 declination, let's go down now to 19. So you'll notice that your time changes as you change your source declination. So I guess in that kind of case, where if you have a wide range in your source declinations or your sources aren't relatively grouped closely together, then yes, you might want to have multiple calculations included. But if all your sources are within the galactic center, or if all of your sources are relatively close by, then I would say 1 is probably fine. It's only if you notice very large changes in your sensitivity calculator, then yes, you might want to include those other ones. Okay, I think there's also a question on the...
Yeah, so there's some ping ponging back and forth, but if we need different sensitivities for different sources, did you just answer that one? Oh, sorry. And then there was, the calculator only shows on source time, correct? Yeah. And how would you recommend estimating / including overhead? Reference the previous shown slide estimates for overheads then.
Okay, that is a great question. Yes, so you'll notice at the very top that you have multiple different time estimates. So you have one that's the derived total observing time, then you have time at signal position or frequency, time at reference position or frequency, and your effective integration time. So what do all of these different time estimates mean? Well, you'll notice that the total observing time is basically the time if you add these two values together. And so if you were doing, let's say a very, very simple observation where you're doing, let's say position switching, you have a single point source, you're pointing on your target, then you're pointing off your target. So basically in this situation, you'd be spending about 2,000 seconds on your target and then 2,000 seconds off your target. So your total observing time in this scenario would be 4,000 seconds. You do not want to be using the integration time when you're doing your time estimates. You want to be using either the signal position or your total observing time. So now if you're doing your signal position time, this type of value is what you would want to be using if you're doing a mapping calculation. So if you're doing a mapping and you're trying to map how much time you need on each position of your map, then you want to be taking this value, and this is the value you will be using for your effective integration time in the mapping calculator. You do not want to be doing your total observing time because that includes time on source and off source. So it depends on the type of observing strategy that you want. If you're doing simple observations where you're just doing on off, or if you're just doing, let's say, for example, a frequency switched observation where you're doing both, signal position or signal frequency and reference frequency, then again, you would want to be using this total observing time. If you're doing mapping, then you want to be using this signal position time in order to calculate the mapping time that you need, with the understanding that if you're doing either, let's say like a reference off, then maybe you need to add in an extra scan or something, for every 3 scans that you have on source. But for the most part, if you're doing your single pointing observations, which are the simplest, then you want to be using this total observing time. If you're doing mapping, then you want to be using this value right here. So I hope that answers your question. If not, I can clarify it a bit more. And I can cover this also a little bit more in the mapping section as well. But that's just kind of a brief overview of what the different time estimates that you have up here are. Okay, well, if there's no more questions on the sensitivity calculator, I will move over to the mapping calculator. Okay, oops, let's use this. And let's see, mapping. Oops, okay. All right, well, I guess we can go ahead and get started a minute early. Okay, so now that we've gone through and done these sensitivity calculations, I want to move on to the mapping calculator, as the mapping calculator will pull information from the sensitivity calculator. All right, so when you should use the mapping calculator. So you want to think about, is your source extended? So if it's extended, then you might want to use the mapping calculator. Are you mapping a region that's larger than your beam size? Where the beam size is shown in the table over here. So if you're mapping a larger region or a region that's larger than your beam size, then yes, you'd also want to use the calculator. But if you're just targeting a point source or an unresolved source, and basically you're either just trying to get a spectrum or get a signal, then you probably don't need to use the mapping calculator. But if you do use the mapping calculator, you want to make sure that, similar to the sensitivity calculator, that all of the results are added in your technical justification as well. Okay, so sections of the mapping calculator. So similar to what we just saw in the sensitivity calculator, you'll have different kind of sections that you will be working through and addressing questions in them. The first being the back end and the observing modes. And then you will identify what type of map type you want to make. So this is the, if you're trying to do either a point map, an on the fly rectangular map, or a daisy map, you need to identify what type of map that you're using, as well as the sky frequency. So the sky frequency determines how big your beam size is. That's where it gets that information, is when you add your sky frequency information in there. It determines basically how much, what the beam size is. And then the integration time. So this is the value that you will get from the sensitivity calculator that we just mentioned. So if you're using, I guess in the previous example that we just went over, this would be where you added that 2000 or 200 seconds per pointing. This is what that effective integration time would be. And then there's row or column sampling versus on the fly sampling, and the number of switching periods. So I'll cover these last three in a bit more detail when we actually go through the demo. But I just want to make sure that you guys are aware that notes for each section or instructions for each section are listed next to their input values. So the example that's given here is for the first one, so the backend and observing mode, that it basically walks you through. If you're unsure, okay, do I need the noise diode on? Do I need to do Doppler tracking? It essentially will walk you through, if you need to select those or not. So it will tell you that if you're doing, like say for example, Vegas spectral line mode, that they recommend, or we recommend that you use the hardware Doppler tracking. So you would basically click on for that one. If you're doing, let's see, noise diodes on for all observations, except for those, so you would want to select that one to be on. Mode would be if you're doing frequency switching or total power. So total power is essentially doing position switching, because you're just integrating on your, getting the total power from the region that you're pointed at. So it will walk you through. If you're unsure of what some of those are, check the instructions that it has next to it, because they do include a lot of that information in there as well. Okay. Oops. All right, so caveats with multi-pixel receivers. So as I guess mentioned at the beginning of the workshop, that several of the receivers are multi-pixel receivers. So for example, Argus, KFPA. And so the KFPA receiver is shown here, where you can see a lot of the positions or offsets between the different beam sizes on the sky. And so if you are mapping a relatively large region, so a region that's larger than this footprint, that your integration time should be divided by the number of beams used in your observation. So why would you want to do this? So this is because as you're mapping over a large region of your target source, that each one of the beams will be passing over most of that region each time. So for KFPA, you would want to divide your integration time by 7 in this case, whereas Argus, since it's a 16 pixel receiver, if you're mapping a region that's larger than the Argus footprint, or at least 2 times the Argus footprint, then you would want to make sure that you divide the time, the effective integration time, or the integration times that you're including in the mapping calculator by 16. Okay, so that's one caveat if you're using multi-pixel receivers, especially KFP and Argus, and you're doing a very large map with using all of your pixels, that you take into account the fact that you do have multiple pixels, and therefore you don't need to be mapping quite as long, because each one of those, you'll be basically adding all of that data together for those. So, and then last part, to make sure that you use the correct values from the sensitivity calculator. So this is one of the last questions that we got about all of the either total time, the time on your signal position versus your reference position versus the effective integration time. So you just want to make sure that for the mapping calculator that you use the correct values from the sensitivity calculator. Okay. So now getting into the different types of mapping strategies that you can do. So the first being on-the-fly rectangle mapping. So one of the benefits of doing the on-the-fly rectangular mapping is that you get uniform sensitivity across the whole map. And so basically that's the example that's shown here for an RA long map, where it's tracing out this red, almost snake-like pattern where it goes back and forth. And you essentially get even sensitivity or uniform sensitivity across your map. And this is one of the most common mapping strategies that's done. I tend to use this a lot for a lot of my observations for extended sources, mainly just because I do like having uniform sensitivity across the whole map. And since I'm not quite sure where some of my sources might be located, detecting some of these dense cores in some of the clouds, I tend to go with rectangular mapping, but it can vary depending on the type of science that you're doing. So if you're doing this type of mapping strategy, you can do both position switching or frequency switching for the scenario. Now, if you're doing position switching, there's two different types of options that you have. One, and this is if you're a little bit more experienced or familiar with the GBT, you can use some of the edge scans or end scans as your off position, especially if it's located well away from some of your sources, that you can use those as almost an off for a reference signal or reference position. Or you can do what's known as an RA long map with reference or a DEC lat map with reference. And so basically there, you give it a certain number of, if I want to do 3 rows and after every 3 rows, take a reference row as being almost an off position. So you can set up your observations that way as well. Or you could do frequency switching. So again, if you have very narrow lines, if you don't have a whole lot of either crowding, then maybe you just want to do frequency switching and just map that way as well. So just because you're doing on the fly mapping doesn't mean you have to do position switching or frequency switching. You can technically do either one. All right, the next option is daisy mapping. So daisy mapping is nice if you want to get really great sensitivity at the center and you have somewhat poor sensitivity near the edge. So this is mainly because you pass through the center, each time you go around in your daisy map, and so you build up a lot of sensitivity or channel source at the very center of your map, but towards the edges of your map, you tend to get much more poor sensitivity. So if you're doing a daisy map, typically this is if you have, if you're doing continuum observations and you want to, reduce the 1/f gain issues that you might run into, daisy mapping might be the way to go. Or if you have a source that's located at the very center and you just want to have as much time as possible targeting that one source, then maybe you want to do daisy mapping. But that's the difference between daisy mapping and rectangular mapping, is even though they're both on the fly and they're both constantly moving, the way that they're doing their sampling or the way that they're doing their mapping of your source is very different. So you want to think about the type of science that you're trying to do for these sources. All right, and then lastly is the point rectangular maps. I mentioned this briefly at the very beginning. So basically a point map is where you sit on a region for a while. So that's what each one of these different X's show is being pointed at a different region on the map. And so you sit there for a while and then you move on to another section, you sit there for a while, you move on to another section, you sit there for a while. And so basically you're just making all these point maps in your observations. And so this is if you need a lot of time on source, or maybe you don't need to do on the fly mapping, that you just want to get very good sensitivity and you want to integrate as long as possible on some of these different sources. So that's what a point rectangular map is doing. And it's different than doing an on the fly map. All right, so to access the mapping calculator, you can use the link that's shown here. Once you click on a link like that, it brings you to a page that looks something like this. Again, where the you have your different instructions for your different input values, which will be listed through each of those. Okay, so now we will go ahead and get started with the live demo. So let me switch back over. Oops. I think I have that open here. Okay. So the mapping calculator, again, you have all of your different types of modes that you can use. So, the Vegas modes correspond to the different types of bandwidths and, spectral resolution that you're interested in. So we'll just pick a random one. But again, this would want to be supported by the types of science that you're doing. Let's say we'll do position switching. And then let's see, we want to do noise diode on. And we will do, since we're doing spectral line observing, we're going to do hardware Doppler tracking on. Oops. There. Okay. And then, as I mentioned, you have your different map types. So we'll just do an on-the-fly rectangular map. Okay, frequency, again, this is where it specifies or it takes in the information to determine how large your beam size is. And so for this one, we'll just do maybe the best frequency of ammonia, which is the example that I was showing earlier. So, yep, 94, okay. Integration time, well, let's see. So let's use that one. Okay, so we'll say maybe 100 seconds on source. Let's ballpark what that would be. And again, this is assuming, okay, if we have, let's say 500 seconds on source, if we're doing KFPA, that's 7 pixels. So I guess maybe it'd be closer to 90 or 80 seconds for your integration time on beam. So we'll just leave it at that for the demo. And then you identify what your map size is. So for us, let's do maybe a 1/2 degree map by a 1/2 degree map. Okay, so then you also have your row or your column oversampling. So this is, I usually just leave this as 1 if you're doing Nyquist sampling, but you can either increase or decrease that value as well. And again, they walk you through different examples of why or when you would want to make changes to that. I usually leave the on-the-fly oversampling default as 2 as well, since that's what was recommended. But again, it gives you examples on when you might want to change that or why you might want to change that. But usually I just leave, whenever I go through and do this for my own data, I usually leave that as the default. And then switching periods. Normally, 4 is usually, again, the recommended default. But it does walk you through also, when you might want to use a, lower value, or if you're doing other types of observations as well. Okay, so you go through, let's say you've added all of the information that you're interested in, and then you click on this button that says submit. Okay. And so then it will give you these results from the mapping calculator. So just to walk you through, it kind of does an overview on your inputs that you added. So what type of Vegas mode you used, if you selected, you know, noise diodes on or off, you know, the observing style. It also goes through and calculates, you know, what your time on per beam was. And so again, we got that value from the sensitivity calculator, as well as what your frequency, your, you know, mapping sizes, all of that information. Okay, these are some very high time on source. So I will go back and change those to make this a little bit more feasible. But you'll see that it gives you the option for an RA long map results and a DEC lat map results. And so, you know, it just summarizes what the, you know, your number of beams per map, as well as what some of the time for the map, as well as the overhead. Now the overhead in this case generally refers to the turnaround time or dump time that you have for your results. This isn't overhead in the sense of, you know, pointing and focus corrections or auto oof corrections or anything like that. This is just overhead in the mapping calculate or the mapping strategy itself. Lastly, that I'm going to cover is that you'll notice that it gives you kind of these outputs here. So these are actually very helpful when you go through and actually set up your observing scripts. So the values that it outputs here, if you're happy with the you know, time on source, you're happy with, you know, the way that you set up your observations, and this can be very beneficial when it comes down to actually setting up your observations, because you could just cut and paste this little script that we have right here, and it will go through and create the map that you set up, as well as giving you the configuration tools that you need for a map of this style. So that can be helpful to include, and we recommend that you include all of this information in the PST as well. So you would want to go through, oops. Let me go through and do this. We'll just copy, oops, receivers, and then mapping calculator and paste those. So we recommend that you include those as well when submitting your proposal, because again, there's a lot of information in the mapping calculator that allows us to go back through and recreate how you got your values or how you estimated how much time you needed to observe or map a region of the sky. Okay, so in this case, oops, let me go back through and make a small change so you can see what it looks like if you do a daisy mapping. So let's change this from on the fly rectangle to on the fly daisy. We'll leave the frequency the same. And then let's do a map size. Let's do 1/4 of a degree map radius. Okay, we'll leave everything else the same, and then we'll submit. Okay, so again, it prints out a lot of the inputs. And then we'll also give you what you would need to go through and create a daisy map for, you know, when you actually get to doing your observations. So including the results from the mapping calculator will help you in the long run when you go to set up your observations, because you can actually just pull a lot of this information from your proposal and just put it into your observing scripts. All right, so I guess we have a little bit more time. Are there any questions, or is there any other type of setup that people would like to see? You know, I can, again, this is meant to help you guys with your proposal setup. So if you would like to see a different observing mode, if you would like to see, you know, different types of parameters. Let me make one change and show you what one error might look like. So if you have a very low integration time, and let's see, maybe a relative, I think it's if you have a relatively small map too. that sometimes you can get an error message, and we'll see. Here we go. Okay, so let's see. Yes, okay. So sometimes you'll get warnings that look like this. A lot of times this is just indicating that, that your lines might be broadened. So it really just depends on, I guess, what your velocity resolution is, on if this will be an issue or not. So sometimes you will see those. I'm not seeing the other issue though. Let's see. Let me try decreasing the integration time. Okay. Yeah, okay. So this is a warning message that I wanted to show you. Okay, so if you have a very small integration time, sometimes you will see a warning message that looks like this. And I typically tend to see this when I use multi-pixel receivers, mainly just because you're dividing by the number of pixels that you have, so it reduces your effective or your integration time. But a lot of times if you see this issue, then essentially what this error message is showing you is that you're bound by the amount of like how fast you can move or how fast you can you know, move or change the telescope or accelerate the telescope when you're doing your observations or you're doing your mapping. So if you see an issue like this, typically that comes in when you are doing that you have a very, very small effective integration time per beam. And that's where that issue comes in. Okay. I think if there's any other error messages that I've run into in the past that I can show you. Okay, so I think there's a question. Okay, it looks like there's a question in the Q&A box. Okay, so this was on the sensitivity calculator. It's the number of spectral windows per spectrometer. Yeah, so going back, I guess, to the sensitivity calculator, I'm guessing that the number of spectral windows that you're asking about is for this one. So for this one, typically this number of spectral windows, it just means how many IFs that you are observing. So if you change those from 1 to 4, it shouldn't change what your time on source is. It just indicates how many spectral windows you're using. So it's not like with the VLA where you have you know, multiple spectral windows in a spectrometer. It's just identifying how many spectral windows that you're observing. So normally if you are setting up your like your observing scripts and your PST, and you identify, okay, that I want, you know, 4 spectral windows, or I want 4, you know, different types of spectrometers, that you want to make sure that you're somewhat consistent across those. But yeah, it shouldn't change what your time is, because those are independent. Okay. I guess any questions in the chat or in the Q&A box? Okay. All right, well, I guess if we can go ahead and get started with some of the ones on the help desk. Are a little bit early now, but I can go ahead and start getting set up for those.
Yeah, while you're setting up, I'll just mention something I put in the chat, and that there's a limited number of accelerations per minute for the GBT. Otherwise, it can shake the feed arm structure too much. And I believe that's typically no more than 2 accelerations every minute. And this is when the telescope turns around in the RE long map or DECLAC map.
Mhm. Yep. All right, well, I guess we can go ahead and get started 5 minutes early on this one. Since this is the last talk, I don't want to just do a short, well, I guess we could do a short break. Maybe we'll keep on schedule. And that way if people want to grab water or anything like that, and I will bring up the slides and get these ready to go. But I think I will wait the 5 minutes until 4:30 and we can get started then for the help desk in case anyone was planning on joining for just that talk. So, but feel free to ask questions on any of the other discussion and topics that we covered. I'd be happy to address any of those questions now, and then we can get started with the help desk and proposal tips here at 4:30. Okay, so it looks like we have a question in the Q&A box. So it says under table 5 in the proposer's guide, it says for modes 20 to 24, the spectral windows must be placed within 1500 megahertz within a usable frequency range of 150 to 1400 megahertz. Does that mean we can't use those modes for say C or X band? Okay, that's a good question. So with that 1500 megahertz range means that all of your different spectral bands have to be within 1500 megahertz or 1.5 gigahertz of each other. So you could use, modes 21 for a KFPA observation at 23 gigahertz. But it would mean that if you had a target line, let's say at 23 gigahertz, that the highest you could go up would be about 24.4. So they have to be within 1500 megahertz of each other. So you can't have one that's at like 23 gigahertz, 24 gigahertz, 25 gigahertz, 26 gigahertz. So you can't go past what that range is. But you can use those higher modes for the higher frequency observations. You don't have to just use them for low frequency. All right, I think we'll give it another minute. If you have any other questions on any of the other topics, feel free to ask those now. Otherwise, we will get started on this next talk at 4:30. Okay, so it's 4:30, so I will go ahead and get started with this last talk. So this will be the last talk in today's workshop. Again, if you know, we will be hosting a second workshop on Tuesday from 9 to 12. This will be almost an identical setup to the one that we had today, covering the same topics, same schedule. But if there's any issues that you run into with creating your proposal, or if there's anything that you would like clarified, you know, feel free to sign up for, you know, that workshop as well. And you can attend whatever talks that you would like to attend in the schedule. Again, we will be trying to keep as close to the schedule as possible. So feel free to hop in or hop out on the workshops to target whatever would be helpful or most helpful for writing your proposals. That's why we're here. Okay, so to go over the help desk. The help desk is basically how you can type up questions or search for previous questions or previous information for different types of, you know, issues with the GBT or doing data reduction or the VLA or CASA or, you know, VLBA. Basically, the NRAO help desk is how you can access any of those. So I'm going to be going into the demo real briefly, and then we will be back to do the outline for the proposal tips. Okay, so let me bring up, see, I have that here, and we will log in. Oops. Okay, well, we will log in this way then. Help desk, log into the NRAO help desk. There we go. Okay. I already have an account. Yes. Okay. All right. So once you're logged into the help desk, you might see something that looks like this. I do have a ticket that's open that I do need to respond to, but I wanted to leave it up so that way you could all see what it looks like if you have a response to a submitted help desk ticket. So again, you can submit your help desk ticket or your question up here. Once you go through and have, let's see, let me show you what it looks like. So we'll click on My Tickets. So all of your previous help desk tickets will be listed. Ones which you have need a response for will be shown at the very top. Resolved ones will be shown below. But it does keep a list of all of your previous tickets that you submitted. So if you wanted to go back and check any of those, you can review those as well. Now, if you want to submit a help desk ticket, you would just click on a button up here. So you can click on that. It gives you the options for different types of topics. And then you'll notice that all of the department descriptions, which you would use for this drop-down menu, will change depending on what topic you're clicking on. So since this is for the GBT, I'm going to click on that. So you'll notice that it gives you all of your options for the GBT. If you have a VLBA question, let's say VLBA proposal review or proposing, you know, you can click on those as well. General inquiries, data products, you know, each one of these different topics will give you a different drop-down menu. So you want to make sure that you select the topic that is most relevant to what your question is. So let's go back to the GBT. I'm not actually going to submit this, but I'm just going to show you what it looks like. So we'll say maybe you have a question on proposing. So we'll click on that, proposing with the GBT. You can type in your subject, your message, and then choose any type of files or questions that you have, and then you can submit a help desk ticket for that. So it's fairly easy, it's fairly straightforward, but I would strongly recommend that being able to narrow down as much as possible the you know, department description or where your question is located or what's most relevant to your question would be the easiest way to make sure that it gets routed to the correct person. We do have a lot of people on staff And so if you have an issue with maybe computing versus proposing versus data reduction, you want to make sure that you are as clear as possible with where you are getting stuck. So that way we can route it to the right person and get you, get your problem solved as quickly as possible. But that's basically how you go through and you create a help desk ticket. It's fairly straightforward. They also have information on, just general either news or general articles. If there's other, general, inquiries or general questions that you have, you can go to, click on your knowledge base, or you could search and it will tell you if this question has been either asked in the past or if they have an article pertaining to step-by-step instructions that could help you. But that's just kind of a brief overview of what the help desk is. It's how you can submit tickets, find general responses or, answers. And they're all identified with different types of, grouped in different types of articles. So once you submit, or if you needed to submit a help desk ticket and you get a response, it will pop up at the very top so that you know that you can check that. Okay, so that's just kind of a brief overview of the NRAO help desk. Do we have any questions on this part before I move back to doing the proposal tips? Again, it's very straightforward. It does walk you through all of the different types of help desk issues. But if anyone has any questions, I'd be happy to either show you those or walk you through those in this demo. Okay, perfect. So let's go back and we will get started on some of the proposal information. All right, so proposal category. So the amount of proposals that we can get varies across different years and different cycles. So across the GBT, NRAO, VLBA, we can get hundreds of proposals that need to be reviewed every cycle. Typically, the review process goes where the proposals for the GBT are divided amongst the GBO staff, scientific staff. We have to make sure that there isn't any conflict of interest between people who might be on proposals, along with collaborators. So there's a very rigorous process just to make sure that there isn't a conflict of interest on who is reviewing these proposals. On average, we can get anywhere from 10 to 20 proposals that are reviewed by the different staff members. We go through and we check your technical reviews. And that's basically where we try to recreate your technical setup. We check to make sure your sources can be viewed by the GBT. We check to make sure that what your proposing strategies are correct. Making sure that you're not asking for 2 prime focus observations back to back. Just a lot of that type of small stuff, just to ensure that what you're proposing to do is capable by the GBT. After that, your proposal is submitted or sent on to a TAC panel. So that's the time allocation committee. And so that is where it's divided amongst different panels who then review it. And then your disposition letters usually come out usually around the beginning part of November. So they can vary. So there is a long process that your proposal goes through. So there are a few very great proposals that we see every cycle. There's a few that are obviously poor, and then the others are sort of in that in-between stage. And so how do you make your proposal stand out? And especially since we are going to be reviewing dozens of these proposals, you want to make sure that your proposal stands out. So some science justification tips. So you want to make sure that you're thorough but concise. And that you have a relevant introduction, that you cover and cite the relevant literature that you need for your proposal, and that you discuss both the potential impact of what a successful result is versus a null result. Because those null results can also tell you something as well. And so you want to make sure that you cover that when you are writing your science justification. You also want to make sure that you don't assume that all referees are experts in your domain. A lot of us will be, especially in the technical justification, we'll be reviewing different types of science that are outside of our area of expertise. I've reviewed FRBs in the past, or proposals that are doing FRBs, and I do star formation. So you want to make sure that you give enough background that someone who is outside of your area of expertise can understand the science that you're doing. So you don't want to blind it with science. You want to keep it simple, but you also want to make sure that you cover enough background where someone who might be unfamiliar with your area can understand what you're doing and why you're doing it. And so you want to make sure that you use or don't use words when a figure would suffice, or vice versa. Sometimes a figure can say 1,000 words, and so you want to make sure that if you're able to explain using a figure versus a whole paragraph of text, that you rate those two options, where maybe sometimes a figure would suffice instead of just a whole block of text. All right, for technical justification tips, so you want to make sure that you are up to date on all of the instrument availability and capabilities. I included some of those in my overview talk at the very beginning of this workshop. If you have any questions, to ask the observatory staff. Again, that's what we're here for. We want to make sure that you get the best possible science from the GBT, and that you're able to understand the best ways to set up your observing strategies and technical setup, spectral setup to get the best and most science out of your observations. Make sure that you provide all of the information that is asked for. In the past, I've seen several technical justifications that have been very short and have missed a lot of the information. And so I had to either do guess and check, to try and see if I could recreate their sensitivity calculations. And there's been a couple times where I haven't been able to recreate their sensitivity calculations based on the information that they gave us. And that had to have been the technical review. So you want to make sure that you provide all of the information that's asked for. And the easiest way to do that is to add in what the sensitivity calculator gives you and what the mapping calculator gives you if you need to use the mapping calculator. So use the tools that are provided by the observatory. That's why they're there. It's to make your life simple or simpler, especially when you're submitting a proposal, and to be explicit about any type of assumptions that you're making and why you're making them. So don't ask for something that is unavailable or impossible. Don't ask for an instrumental setup that is not justified by the science. And then don't pad your time request. We do conduct an independent review. So that's what we're doing when we're doing our technical review, is being able to calculate your time on source, the time that you're needed, and cross-checking that with your sensitivity. So don't pad your time. We do check for that. So make sure that the way that you're setting it up can be recreated and is consistent with the information that you're providing. So general proposal tips, you don't need to repeat the abstract in the proposal. So this is in your science justification. I've seen people in the past sometimes put their abstract, at the very top of their science justification. And you don't need to do that. It is on the cover sheet. And then the same thing goes for your technical justification. Those have a unlimited page limit for your technical justification. So you don't need to recreate everything in your science justification, since you only have 4 pages for that. You don't want to get bogged down by your abstract or additional information that is going to be going in the technical justification, or that can be in the technical justification, and just repeating yourself and losing some of that space that could be dedicated towards science. Don't add content just to reach the page limit. So there is a 4 page limit for the science justification. So you don't want to just add content to reach the page limit. You don't need to do that. Again, if you can get your science across and convince a reader why your science is important in 3 pages, that's fine. So don't feel like you have to fill in the 4 pages if you don't need to. Make sure that you follow all of the formatting guidelines. So the 4-page limit for regular, triggered, or DDT proposals, the 10-page limit for large proposals, which again are only accepted in the February deadlines, that these include all figures, tables, references that you need. They all have to be within that 4-page limit. That all of your proposals have a minimum of 11-point font for the main text. If you want to go a little bit smaller for, let's say, your figures, footnotes, maybe some references, that's okay, but just make sure that it's still legible and that you're not going super, super small for those. And lastly, all proposals need to have the 1-inch margins around the edges as well. And so just as a last reminder that referees, both us on the technical review and in the science review, we read lots of proposals. So you want to make sure that yours stands out, you make it exciting, and why people from different scientific backgrounds should care about the science that you're proposing to do, why it's important, motivating your research and motivating your observations. So the proposal tips. So as I mentioned, we have a panel-based system. So there's 8 different panels for the TAC, and there's a broad community representation on these panels, as well as non-experts on these panels. So you could have people who might not be experts in your field reviewing your proposal. So that's why you want to make sure that you do cover enough background information so that they're almost brought up to speed on the science that you're doing, that you're motivating with a overarching scientific question that's motivated on why this is important for your field, and just covering that type of background. The proposals are ranked from 0 to 10, with 0 being the best, 10 being the worst. And at the end of your proposal, when you get your disposition letter, you will be given one of 4 letters, A, B, C, or N. A means that it's active for up to 1 year. So that's basically where you're covering 2 cycles. So if you, say, for example, had an A-ranked proposal this cycle, that your proposal would basically be open or could be observed from February 1st, 2022 to February 1st, or I guess January 31st, 2023. So it'd be active for a year. If you have a B or C ranked proposal, those are only active for 1 semester. So if you got a B or C ranked proposal this current cycle, then your proposal will be active from February 1st to August 1st. With B generally being that you'll probably get on the telescope, and C is usually filler time proposals. So if they need to fill in a proposal for filler time, which means that you might not get the best weather, you might not get the best, observing time, but we try and schedule those as well. And N just means that it was not accepted, sometimes due to scheduling conflicts, sometimes due to the proposal ranking. You could have a high-ranked proposal that still doesn't get accepted just because of overcrowding at a certain LST range. So just be aware of that. All right, so continuing GBO proposal tips. So if you're in doubt about something in the proposal or parameter or your setup, feel free to contact us. That's why we're here. We're here to help you submit your proposals. So if there's something you're unsure of, feel free to contact one of us on the scientific staff. We'd be happy to walk you through it. As I mentioned earlier, your technical justification is unlimited space. So you want to make sure that you're addressing what you're using. So like what instruments you're using, which receivers you're using, how you're using it, how long you need it, and how you determine those values. Make sure that you include your overhead times. We went over your pointing and focus corrections that you need to include, and how often you need to include those, as well as your auto oof if you're doing high frequency, and then just some, you know, scan latencies. So dump time, you know, countdown time for starting a scan, slewing, a lot of those different things can account or add into your overhead times as well. All right, so common mistakes. So the confusion limit. So basically this is where, you know, if you have multiple sources in your beam, that can add to your confusion limit. So once you hit the limit, you're done. And this is unless you have knowledge of the emission at higher resolution. The 1/f noise, your gain variation. So this is your receiver dependence. And it's relative to the product of your bandwidth and your total integration time, exceeds certain limits. So basically the 1/f noise is where you almost reach kind of a block where adding in larger bandwidth or adding in larger time on source is not going to improve your sensitivity. You also have RFI to make sure that you account for any type of RFI, you know, that you have, you know of any types of RFI emissions that could be in the, you know, receiver that you're observing or the spectral window that you're observing, and that you have a plan for how you want to mitigate those. So maybe you want to do, you know, different types of polarization where RFI will show up in one polarization versus the other. That you have kind of a plan for how you will account for RFI that could be in your data. And then again, use the sensitivity calculator, use the mapping calculator if you need those. That's why they're there, is to make your life simpler, so that you don't have to use you know, equations to go through and calculate your sensitivity. You know, that's why we have the calculators to help you all be able to submit your proposals. So if you need them, make sure that you use them. All right, so I think that kind of wraps up the last part of the workshop. So we've covered the overview of the GBT science, the GBT capabilities. We went over a demonstration of the PST, the sensitivity calculator, the mapping calculator, the help desk, and then wrapped up with some tips for a good proposal. So now, wanted to give just a little bit of time in case there was any type of questions that we didn't get a chance to address earlier in the workshop, or if there's any final questions that people have, or if they've tried walking through any of the, you know, demos or the PST or calculators and have gotten either an error message or gotten you know, stuck in a certain part, you know, feel free to ask those and we can, you know, help walk you through those. Again, this is just to help you guys submit a proposal, be able to help you guys with setting up your observations and stuff. So are there any other final questions? All right, is it true that proposals with less time needed have more of a chance of getting accepted? Maybe if Tony's still online, he might be able to ask. So,
Yeah, I don't believe that's necessarily true. I've never really seen a correlation between the requested time and the number of proposals accepted. It's almost always based on how well the proposal is written.
okay, any other questions? Any additional discussion? Okay, well, if there's no other additional questions, I guess we can wrap up here. I will probably stay on until 5 in case anyone, you know, wants to either ask a question or anything like that. But I think if no one has any questions, I think we'll wrap up.